Now we need to take a slight detour and talk about independence a little bit more. So there's a rule of thumb for faking independence, if you will. So, and this is a rule that's going to come in handy in chapters 8 and 9 and 10 and so on. So if we have small random samples that are taken from very large populations without replacement, so we're not putting them back, it is reasonable to assume independence of the events. As a rule of thumb, if the sample size is less than 5% of the population size, and the way we notate that is little n, which is the sample size, is less than or equal to 0.05 capital N being the population size, whatever that may be, we can treat the events as independent. So this little idea, especially this bit right here with the little n less than or equal to 0.05 capital N, that's going to show up a lot in chapters 8, 9, and 10. So, and beyond, if you go beyond. So we need to kind of understand what's happening here. So let's suppose we have a bulk bin of M&Ms at a large candy store. So you walk in, big candy store, there's a bin full of M&Ms, just full of them, right? So it has 2,500 plain, regular color, normal M&Ms, which is equivalent to about a 5-pound bag. And then you know somehow magically, because you've got that kind of power, that 500 of those candies are orange, right? So huge, huge bin, all mixed up, but 500 of the candies in there are orange. Now you're going to reach in and you're going to take 2 M&Ms at random. Now, those colors that you take, you choose 2 at random, those 2 M&Ms are dependent, right? Because drawing the first candy fundamentally affects what's left in the bin. There's only 2,499 left after you take that first one, right? So these are truly dependent, right? You draw a candy, you're affecting what's left, and so on. All right, now let's find out the probability that both of them are orange. You're going to draw 2 candies at random. What's the chances that you're going to have orange and orange? So let me type that up. All right, so I want an orange, O, orange, on the first and an orange on the second. Well, according to the general multiplication rule, that's the probability of an orange on the first one times the probability of an orange on the second one, given that I've already drawn an orange on the first. In other words, I want to draw an orange and draw an orange, right? Okay, well, the chances of drawing the first orange, there's 500 of them out of 2,500, right? So I have a 500 out of 2,500 chance of drawing that first orange. Now, after I've drawn it, there's only 499 orange ones left out of 2,499 left in the bin, because I'm so crafty I have taken it out of there. All right, well, if I multiply both of the numbers, 500 times 499 is 249,500. And then, let's see, 2,500 times 2,499 is 6,247,500. These are huge numbers, very hard for us to kind of get a mental picture of. So we are going to use a decimal instead. And it said to use 6 decimal places. So we're going to do that, 0.039936. All right, so that seems reasonable. I mean, it's a lot of decimal places, but okay. Now, what was the sample size and what was the population size? And do we in fact satisfy this condition of little n being greater or less than or equal to 0.05 capital N in particular? All right, well, let's see here. Let's start with little n. Little n is our sample size, which was 2, right? Capital N is our population size, which is how many there are in the bin, which is 2,500 originally. Right? So now we have to ask ourselves, is little n less than or equal to 0.05 capital N? So in order to do that, what we really want to know is 2 less than or equal to, there we go, 0.05. Now capital N, they write it like that, but what they really mean is multiplication. So I need to multiply 0.05 times 2,500 and I'll find this out. So matter of fact, let's just do it that way. I'll do it right down here. So let's see. 0.05 capital N is equal to 0.05 times 2,500, which according to my calculator is 125, right? 2 is definitely less than 125. So yes, right? 2 is less than 125. Therefore, little n is in fact less than or equal to capital N. So there's the answer to the third part. And then up here is the answer to the first two parts, right? Little n and capital N. All right, so what? So we know that little n is less than or equal to 0.05 capital N. Now, according to the table up here, the rule of thumb up here, it says if it is less than 5%, we can treat the events as if they're independent. See that word right there? Interesting. So let's go back and assume that the two random M&Ms are independent right here. And that's the key word, independent. All right, well, if we treat them both as independent, then that means that I'm going to not have to bother with this whole second given the first thing, right? So I'm just going to say, what's the probability of an orange on the first times the probability of an orange on a second? And I won't need to worry about an orange on the first because they're independent of each other. So therefore, this part disappears. In other words, I'm going to treat it as if there are 2,500 M&Ms in the bin both times, even though there's not. Technically, there's really 25 or 24.99, but I'm going to treat them as if they are. Well, how does this change the answer? The numerator is 2,500, the denominator is 6,250,000, and the decimal becomes 0.04 when you work it out with a calculator. All right. So notice how close these two numbers are. I mean, look at this. When you treated them as if they were dependent, right, you got 0.039936, which is a very small number, right? And when you don't treat them as if they're dependent, when you treat them as if they're independent, you get 0.04 right here. That bit, right? They are extremely close. And basically the box at the top of the page is saying, it's close enough, right? We're faking independent, right? As long as your sample size is really small in comparison to your population size, then you can treat them like they're basically independent of each other. And that's the moral of the story. Since n equals 2 is so small in comparison to capital N, which is 2,500, the probabilities we find here in letters B and D, the green ones, are barely different from each other. Here, I'll highlight that. Right? Those probabilities we found are so similar. But the D one, the second one, is actually easier to find because it doesn't involve a conditional probability. You just treat it as if every draw is the same. 500 out of 2,500, 500 out of 2,500. I mean, as long as you're taking a very small amount, why not use that probability, that calculation, this second one right here? Because this is a whole lot easier to do than this one, which involves that conditional probability where you have to sit there and try to figure out, okay, I drew this many, how many are left, and blah, blah, blah. But if you say, well, it's close enough, let's just treat them like they're independent, that's going to make things easier for us. And that's why we need this later on when we start working with more difficult problems. We want to be able to do these easier probabilities, and treating them as independent will be one of the keys to that. But we can only do it as long as little n is less than or equal to 0.05 capital N. If that condition is not met, then we can't do this fake it, make it independent-ish. By the way, every little kid in the world knows this idea because if you take a little small child in front of a bulk bin of M&Ms, they're probably going to try to snitch one, right? Because they don't think you're really going to notice. Exactly, right? If your sample, if that one M&M is so small in comparison to how big the tub is, who's really going to know, right? And that's the same rule that we're applying here in a way to this sample and population size. If your sample size is so small, who's going to know? Treat it like it's independent and move on. Now remember this when it comes back in section 8.2, because it will come back.